Hello everyone, welcome to lecture 5 of week 2 of the course Simulation of Modern Power Systems. This is the last lecture of week 2 and we will continue the discussion on the module power flow analysis. To be specific, we will rediscuss the application of Newton-Raphson method for power flow equations when bus voltage phasors are written in rectangular coordinates. The complex bus voltage phasors are denoted in the form of rectangular coordinates. That is, if Vi is the voltage phasor of bus I, then it is represented as a real part, which is Ei, plus J of Fi, where Fi is the imaginary component and J is the complex operator root over of -1. The last discussion was on Newton-Raphson method itself, where bus voltage phasors were written in form of polar coordinates, that is, voltage at bus I, the complex bus voltage phasor, was mentioned or written as Vi magnitude with an angle of theta I, where theta I is the voltage phase angle with respect to the angle reference bus or the slack bus. In polar coordinate version of bus voltage phasors, the corresponding power flow equations were transcendental equations. By transcendental equations, I mean the P and Q expressions, they were having sine and cosine terms of voltage phase angle differences. On the other hand, when voltages are in rectangular coordinates, the same equations, instead of being transcendental, would convert into quadratic equations, and hence the method remains the same, but the corresponding function f of x, the associated unknown x, as well as Jacobian matrix is going to change when voltage is written in a rectangular coordinate version. We will also see an example of how this method works when voltage are in rectangular coordinates. The last discussion on polar coordinate, we had seen an example also. So my request to all is that just not following the slides or the discussions that we have been having, it would be very important if you can also do practice based on the example that I have discussed and the examples that I'll discuss further on. That will give you a better understanding of how these methods work. In fact, the solutions that I have shown for previous examples as well as the examples that are going to come, the solutions have been obtained in a computing platform known as MATLAB, which is a very well-known tool used in simulation of modern power systems. There are other advanced simulation tools compared to MATLAB, like real-time simulator, PSCAD, Dixilent. But for steady-state studies, MATLAB simulation tools or MATLAB platform with code written on it in MATLAB.m file, it serves the purpose. So how things look in form of voltage phasors being written as rectangular coordinates. The complex power expression, it remains the same, and the bus injection at current injection at bus I, it also remains the same. That is, it can be rewritten in terms of bus admittance matrix elements and the other all known unknown voltage phasors. The difference here is that, as I mentioned, Vi, instead of being represented in polar coordinate, it is being written now in form of rectangular coordinate. And same notion if we apply to all voltage phasors, and if we substitute the corresponding terms, then the complex power injection, the conjugate of complex power injection, it gets rewritten in form of E's and F's, and capital G and capital B, they are the real and imaginary parts of the bus admittance matrix. To be precise, I comma kth element of the bus admittance matrix is nothing but Gik plus j bik, where j is the complex operator, that is root over of -1. If this is the expression of complex power injection, then from this I can extract the real power injection equation, which is going to be the real part of SI conjugate, and I can also get the corresponding imaginary part with a negative sign. Reason being, I am taking the conjugate of complex power as the argument of the imaginary function. So, if I do that, then I get the real power injection equation and the corresponding reactive power injection equation. The negative sign which is mentioned here is the same negative sign as it is appearing here. Please spend some time on cross-checking the sanctity of these equations. I am sure you will be able to match the expressions from the complex power injection equations. So, as you can see, as I mentioned, the power flow equations P's and Q's, they are all quadratic expressions of E's and F's. Y-bus matrix is known, as a result of which G and B elements are known. The unknowns are E's and F's, and they are appearing in products, and that is what gives the expression of P and Q to be a quadratic expression. And hence, as you can see, if P's and Q's are quadratic expressions, it is evident that the unknown vector has to now change. The mismatch or power flow equation vector f of x now has to change, and corresponding j also has to change. Given the power flow equations, we will understand in the next few slides what these x, f and j would be. But suppose we know that, then we will be able to solve these power flow equations, and once we solve these power flow equations, we get all our unknowns x, which are essentially in this case combinations of E's and F's at respective PV, PQ buses. And once we know these states, we know all bus voltage phasors, using which we can then find the corresponding line flow, the currents specifically, and using the current expression we can also find the corresponding real power flow and reactive power flow on a line which is present between bus I and bus K. Bus I is often called as the sending bus, and bus K is consequently the receiving bus. Different textbooks or literatures may also call this to be the from bus and the receiving end to be the to bus. Now, I would like to spend some time on these expressions of real and reactive power flows. The derivations of these, they remain the same as we saw the polar version of these expressions, wherein I assumed that the current on a line between bus I and K, it is Vi minus Vk multiplied by Yik. The small Yik indicates the actual line and admittance based on the nominal pi modeling of the line, plus half line charging susceptance because of this line multiplied by the corresponding node voltage phasor. Now, how do I get this current expression? The diagram of nominal pi model would make it very clear that if I am representing my nominal pi model as a lumped representation, which is true for steady state analysis, then the series admittance is Yik, which is inverse of the series impedance, and in pi model we will also have half line charging susceptance on both the ends of the line. So, Bik sh by 2. If I have to find, and after I have done the voltage evaluation from power flow analysis, I also know what is the voltage at bus K, what is the voltage at bus K, bus I, bus K respectively. If I have to find the current, which is Iik, whose expression is given over here, which is the current from bus I to bus K, then having drawn this diagram, the evaluation of Ik is simply application of KCL at this node, which would give me this expression. On similar lines, we also have reverse currents, which I can mark as IKI, which would be, by application of KCL, would be Vk minus Vi into Yik plus half line charging susceptance by 2 into Vk. The term of half-line charging susceptance is what creates the difference in the incoming and the reverse currents. If half-line charging susceptance is not present, then the IK current and IKI current, that is forward and reverse current, they would be equal in magnitude or phase angle also, with the reverse phase angle. Now, this is all true when I have discussed about a typical transmission line modeled as nominal pi model. I did not explain how would you find the current in a section or across two buses which are connected through a transformer tap, based on which the corresponding PIK and QIK expressions are going to be different if we have transformer taps present between bus I and bus K. What I'll do is, I'll request you all to please take a look at the discussion where we had discussed about consideration of transformer taps between bus I and K, depending on the position of tap present between bus I and K. So let me probably draw the diagram. If I have bus I and bus K, which is having a transformer tap with the corresponding leakage admittance or reactance marked as YIK of the transformer, and the tap is at bus K side, then with the reference given to the consideration of transformer tap discussion, you would very easily be able to see that we had written the expressions of II and IK. In context of those II and IK, we can now easily write that IIK, which is flow of current from bus I to bus K, is nothing but II, which is going to be equal to Vi into Yik minus Vk into Yik by A, where A is the corresponding transformer tap. And similarly, the IK current would be IK equal to minus Vi Yik by A conjugate plus Vk Yik by A square. So, for transmission lines which are similar to transformer taps with tap is equal to 1, the previous current expressions that I wrote, they would simply boil down to the same expressions, difference being that half-line charging susceptances would not be present. But even if, let us say, theoretically we have a transformer tap along with nominal pi model of line superimposed, then these expressions would also have the corresponding half-line charging susceptances present, as we have seen earlier, which I am not going to write in detail. But given these current expressions, you can then find the forward flow of power, which would be SIK is the complex flow of power from bus I to bus K, which would be Vi into IIK conjugate. If IIK is to be replaced in terms of this conjugate here, you would see a difference in these expressions of P's and Q's. The difference would be that you would also have presence of transformer tap A in these expressions. I leave that discussion or exercise to my viewers to please evaluate those expressions and let me know in case there is any doubt or confusion in evaluating real and reactive power flow for transformer taps present between two buses. Having said that, the next few expressions or powers that we can obtain would be the slack bus power, which is slack bus generation, both P and Q in terms of their injections. And given the presence of load at all, if at all, at the slack bus, we will be able to find the corresponding real and reactive power generation. Similarly, we can also find the expression of total real power loss as well as the reactive component using the corresponding E's and F's, which have now been obtained after rectangular version of power flow equations being solved in Newton-Raphson method. So, to verify or confirm the details of how Newton-Raphson would look like when voltage phasors are in rectangular coordinate, we will start with the same assumption, that is, for the sake of convenience, I would choose bus 1 to be a slack bus. Please note that when I define a slack bus, I would essentially need a generator to be connected to it. And with the discussion that we have had in the past, that generally the bus to which the largest generator is connected, the corresponding bus can be considered to be a slack bus. If at all, given the data sheet, if bus 1 is not a slack bus, then definitely there would be some slack bus or a bus where the largest generator is connected. These bus numbers can be interchanged with corresponding changes also happening in the line data specification, and eventually we can have bus 1 to be the slack bus. Since bus 1 is a slack bus at which the voltage is specified, because it is a bus to which a generator is connected, so we can easily define that the real part of voltage would be same as the specified voltage, because it is convenient to choose the phase angle reference of bus 1 angle to be 0, which results in corresponding F to be 0. Why is that? If I write the generic expression of EI and FI for a voltage phasor at bus I, then in terms of polar coordinates, EI is VI cos theta I and Fi is Vi sin theta I. If I choose theta I for the angle reference bus to be 0, no matter what the voltage is, then the corresponding F will be 0. And if F is 0, the angle is 0, in that case cosine becomes 1, and that's the reason why E1 is same as the voltage magnitude itself, which is the specified voltage. For PV buses, voltage magnitude is specified. That is how the voltage control or reactive power control or excitation control of generators work. But then the problem in rectangular version is we don't have variables explicitly for PV buses which would ensure this condition, that is voltage magnitude for a PV bus, it is to be fixed because it is specified. So what do we do? That is where the difference in f of x comes in. To ensure that the voltage magnitude of PV buses is specified, we bring in this additional equation which was not present in the polar version of Newton-Raphson power flow, so that for PV buses this condition is true at the final convergence, because we want f of x to be 0. So if f of x becomes 0, the third set of equation also becomes 0, essentially leading that for PV buses the corresponding E's and F's should take such a value so that the Vi specified value is specified. Now where is this equation coming from? I have already given a reasoning for that. That in terms of polar coordinates, I can write what my rectangular coordinates are, and if I have to get rid of the phase angle theta I, I'll square these components and eventually I would get Vi square, which is essentially the rewritten form of what you see for PV bus equations. The other two equations, P's and Q's, they remain the same. Difference is only that the expression of Pi and Qi are now quadratic expressions of E's and F's. So essentially what do we see in terms of polar version of Newton-Raphson method? How many equations do we have? We have n minus 1 number of P equations, because for bus 1 it's a slack bus, so no power flow equation should come at all. Then we have Q equations for PQ buses. So if let's say I have ND number of PQ buses, then Q's are ND. And then the last equation of voltage form, which is only for PV buses. If I have ND number of load buses, then essentially I have n minus 1 minus ND number of PV buses, because bus 1 is slack bus. So if I see that this is the number of equations that I have, and if I add them up, then essentially I have 2n minus 2 number of power flow equations. Whereas in polar version, this is for the rectangular case, in polar version I had n minus 1 plus ND number of equations in polar version, because there was no need of these expressions in the polar version. The first two equations, they were the similar forms in polar version, and that is where the difference comes in. So it's imperative that if I have 2n minus 2 number of known equations, how many unknowns would I have? What would be the value or size of x? That is evident here as shown over here. For all PQ and PV buses, E's and F's are unknown. because for PV buses, voltage magnitude is specified. That doesn't dictate that E and F can be fixed a priori. And that is the reason why we have n-1 Fs, n-1 E's, which again add up to 2n-2, consistent with the 2n-2 equations that are involved in rectangular coordinate version. Like in Gauss-Seidel and Newton-Raphson version of polar coordinates, we can easily start with a flat start of voltage, wherein all my imaginary parts would be 0 of voltages, and the corresponding real parts for PQ buses can be chosen as 1, and for other PV buses they can be set at their specified voltage magnitude. Once these initial choices are known, I can find what f of x0 is, and if f is 2n-2, x is 2n-2, it's obvious that J would also be a 2n-2 cross 2n-2 matrix with 6 submatrices. In polar version of Jacobian, we had 4 submatrices because there we had voltage phase angle and magnitude of voltage as the unknowns, and we had only P and Q expressions. That is what brings in 2 cross 2 4 combinations. In rectangular version, we have a P equation, we have a Q equation, and we also have a voltage equation for PV bus, and we have unknowns as F's and E's. So we have 3, 2, which is 6 combinations, which is what is resulting into these 6 submatrices. Having known the expressions of P, Q and V, the V form is this expression as written over here, whereas the P expression is shown on slide number 3 as already explained. I can then easily evaluate what would be the submatrices, that their dimensions, while ensuring that the overall dimension of Jacobian is a square matrix of 2n-2. The convergence criteria on tolerance check for updates, it remains the same as we discussed for polar analysis. So dimensions of JPF is n-1, n-1, because I have n-1 P's, I have n-1 F's, and the corresponding expressions are given here for diagonal and off-diagonal terms. Same is the case for JQF submatrix, JVF submatrix, and so on for JPE, JQE, and JVE submatrices. Please spend some time on verifying and evaluating these expressions. I'm sure you will be able to match these function evaluations with respect to the different terms that have been mentioned here, both from off-diagonal and diagonal perspectives. So, coming to the last part of handling PV-PQ switchings in Newton-Raphson polar coordinate, Newton-Raphson power flow with rectangular coordinate. The process is exactly the same, the theory exactly remains the same. For every PV bus, a check has to be made whether its voltage magnitude can remain fixed as long as its reactive power generation is within the minimum and maximum generation limits. If it is not so, then the PV bus converts to PQ bus. Then in the next iteration of rectangular coordinate, for every converted PV to PQ bus, a check has to be made whether the converted PQ bus can regain back its PV status, for which we update its voltage magnitude, that is, we correct its voltage magnitude, reevaluate the reactive power generation, and check whether it is again back to its limit. If it is back to its limit, the converted PQ bus converts to PV bus and corresponding equations change. So what are those equations? In rectangular version of Newton-Raphson power flow, during PV to PQ switching, instead of voltage equation, which is evident or present for PV bus in the conventional case, instead of voltage equation, now we will have the reactive power injection equation. And from PQ to PV switching, where it was already a PV bus already, instead of the Q expression coming in, we will now bring in the voltage equation. So when I say that we are bringing in the reactive power injection equation, in that I mean that for Qi at the converted PV to PQ or PQ to PV bus, the basic analysis or principle says that Qi should be equal to Qgi minus Qdi, which I can rewrite as, at convergence, Qi should be minus Qgi plus Qdi. Now suppose there is a PV bus, ith bus, for some iteration of rectangular version of Newton-Raphson power flow. Qgi is trying to violate the maximum limit. voltage control, reactive power control will not allow that to do so. So, we set QGI to its maximum value, and in that case this expression which is being present over here, written over here, gets converted as QI minus QGI upper limit, which we know a priori, and presence depending on the demand present on the PV bus, we get this expression which is similar to what we saw for other PQ buses. Same is the case when QG tries to violate its minimum limit. In polar version of Newton-Raphson method, we saw that the number of equations change, as a result of which the Jacobian dimension changes. In rectangular version, however, the equations change, but the Jacobian size will not change. It always remains 2n minus 2, 2n minus 2. With the difference being that the elements has to change, so Jacobian elements have to be re-evaluated and rechecked ever. In terms of convergence, I have already explained in the previous discussion that Newton-Raphson has better convergence than Gauss-Seidel method. It has quadratic convergence, and given a well-defined system where the system load is not very high, Newton-Raphson takes 6 to 10 iterations to converge to find its solution. Usually it gives the high voltage solution, that means voltage magnitudes tend to be close to 1 per unit. Given a quadratic expression, it has two possible routes. In power flow equations, we prefer operating at voltage magnitudes being close to 1 per unit, which is we call as the high voltage solution. Mathematically, however, there can also be a solution where voltage magnitudes tend to be closing to 0 per unit, and which is what is called as the low voltage solution. We will discuss more about high voltage versus low voltage solution when we discuss voltage stability analysis module at length. In voltage stability analysis, essentially what happens is, depending on the increase in system load, high voltage solution starts moving towards the low voltage solutions. And in fact, depending on the initial choice which we feed to Newton-Raphson power flow, there can also be a possibility that our power flow analysis gives us a low voltage solution. There are well dedicated research papers on this which talk about the behavior of Newton-Raphson technique depending on the initial choice. For ill-conditioned systems, which is what I mean by high loads or high R by X ratios for distribution systems, radial systems like Gauss-Seidel method, Newton-Raphson also has convergence issues due to ill-conditioning or singularity of Jacobian. And we have also seen in the previous discussion that Jacobian being a large matrix, so its factorization and computation is a burdensome exercise, which is where we will take up the topic of decoupled and fast decoupled technique, where the repeated evaluation of Jacobian is avoided in the next to next discussion. I will conclude this discussion with an example. I have a similar 3-bus network where bus 1 is slack bus 2 is PQ bus 3 is a PV bus. I have intentionally changed the system data a bit in comparison to the previous example that we saw for Newton-Raphson method. The line resistances were 0, whereas in this example I have taken it to be a lossy system. There is a reason why I have chosen this. It will become evident in the next discussion. And additionally, I have also assumed the presence of a shunt capacitor whose admittance is given at bus number 2. And the load at bus number 2 is 1.5 plus J2 per unit. The previous example, the 2 per unit load was 1.5 per unit. And generator at bus 3, instead of generating 1 pu in the previous example, is now generating 0.5 pu. Now, why have I taken this shunt admittance intently here? So for this given 3-bus network, if I apply my Y-bus discussion, I will get a 3 cross 3 Y-bus. In the absence of line resistances and this shunt capacitance, the previous Y-bus that we got in Newton-Raphson polar version, in that Y-bus was a singular matrix. If Y-bus was a singular matrix, that means we have also discussed the implication of singularity of Y-bus. If Y-bus becomes singular, bus impedance matrix cannot exist, and a non-existence of bus impedance matrix, we have discussed in the initial discussions on power flow that we won't be able to find unique bus voltage phasors or unique bus injection currents. Despite that discussion, the previous example in Newton-Raphson polar version, we had a singular Y bus and we were able to get the converged voltage phasors of all buses. We were able to find the currents. Now, the question that remains here is how? If Y bus is singular, how did power flow analysis give a voltage solution in the first place? The reason or the answer to this question lies in the fact that in this 3-bus network or for general power network, we do have slack buses and PV buses where the voltage magnitudes are specified. If at all a case comes where all PV buses switch to PQ buses, we will still have the angle reference bus whose voltage magnitude would be known. And this specification of voltage magnitude lets power flow know what should be the mathematically correct high voltage phasors at all of the buses. And hence, singularity of Y bus, which essentially indicates that network is unconnected with ground. No matter the ground is unconnected, we are providing physical inputs in terms of voltage phasors, specifically magnitudes, which helps power flow converge to a solution. And that's the reason why power flow for Newton-Raphson polar version was working and converging to a solution. Coming back to the question that we have here, the next paragraph here essentially sort of summarizes the inputs that we have got. We'll choose rectangular version of bus voltage phasors, as a result of which the unknowns for this 3-bus network are the 2 F's and the 2 E's. We can use the flat start of voltage for the initial choice. The equations that we have, f of x, they are this equation. This term and this term are PD2 and QD2, whereas this term here is PG3. 1.05 is the voltage magnitude of the PV bus at bus number 3. The expressions of P2, P3 and Q2, they can be checked and verified for this 3-bus network. Intentionally, G and B elements have been mentioned because compared to previous example, G and B, they are non-zero elements. With this initial choice, if we find the injections, then P2 0, P3 0, Q2 0, they are these values. We also make a check at bus number 3 whether it can remain as a PV bus. Since there is no load present at bus number 3, so QG3 is 0.3891, which is within its limit of Qmin and Qmax, and hence bus 3 would remain as PV bus, and that's how the f of x notation is perfectly correct. So if we find the mismatch vector, this is what the mismatch vector is. We can use the expressions of Jacobian elements. I have shown this for few elements. Please check and verify for other elements. The Jacobian would be a 4 cross 4 matrix. N is 3, so 2n minus 2 is 4. The first row is for P2. The second row is for P3. Second row is for Q2. And the last row is for the voltage magnitude specification of bus number 3, where the columns are F2, F3, E2 and E3. Since voltage of bus 3 has nothing to do with F2 and E2 mathematically, that's the reason why these elements are 0. Voltage at bus 3 has to do with F3 and E3, but since F3 is initially chosen as 0, which is mentioned over here, so that's the reason why this Jacobian element also becomes 0, and 2.1 is because 2E3 0, where E3 is 1.05, is essentially 2.1. With this Jacobian after first iteration, if we put in those numbers appropriately, do the matrix multiplication, this is our final first iteration solution, from where this number is F21, F31, E21 and E31, which is what these voltage phasors are. Finally, the solution converges in 5 iterations with tolerance of 10 to the power minus 4, and eventually bus 3 switches to PQ status in second iteration with never ever coming back to PV status. That is the reason why V3, if you evaluate its voltage magnitude, V3 won't be equal to 1.05. The corresponding generations can then be evaluated. As you can see, PG3 is 0.5, demand is 1.5. So bus 1 is generating more than 1 per unit, with 0.4245 being the system loss. Similarly, we have reactive power generation. Bus 3 cannot exceed 1 per unit maximum limit, so it is remaining at 1 pu, because this is also equal to QG3 max. Similarly, you can find the corresponding complex power flows, both the forward and reverse flows. And eventually, if you add these two flows, you will be able to find individual line losses. These line losses together added results in the total system loss, where this is P loss, total system power, active power loss in the overall network. With this, I conclude this discussion, and the next discussion will be on participation factored power flow. The basis of participation factored power flow is that why should there be only one bus acting as slack bus? Why should only one bus be responsible for taking up the mismatch between generation and load as well as system losses? Is there a better way of minimizing this dumping behavior? Is where participation factored power flow comes in, which draws its inspiration from economic dispatch. So I'll also briefly touch on the economic dispatch aspect in the next discussion. Looking forward to more discussions. Thank you.